let's look at our last group of compounds to name: carbonyls and carboxyls. Carbonyls have CO, carboxyls have CO2. So here they are, a bunch of functional groups that we learned at the beginning of the term. Most of them are related, most of them are derivatives of carboxylic acids themselves. We'll learn about the reactivity of these quite a bit in organic too, a lot of us will. But for now, we are going to name them. So let's start with carboxylic acids and carboxylates. So the carboxylate ion is simply the conjugate base of the carboxylic acid. Remember that these are really weak acids overall. So they're strong acids in terms of the general organic compounds that we're looking at, but they're weak acids in the sense that they are not fully dissociated in water. pKa 5 is like 0.001% dissociated in water. So for the most part, they are neutral compounds. Okay, so throughout this video, I'm going to put some compounds in green boxes. Those you should memorize. I'll be able to fit all of them on one slide at the end to kind of keep them all together. It's not a massive list, but it's just plain useful to know a few molecules without having to look it up. So these are the two simplest carboxylic acids, methanoic and ethanoic acid, which nobody calls them. They are formic acid and acetic acid. Formic acid, if you've ever, when you're a kid, grabbed just a handful of ants and put them in a blender and just kind of ground them up, and you smell that is formic acid. Or what red ants use to sting people is formic acid. Acetic acid is vinegar, so household vinegar is about 5% acetic acid. Benzoic acid is there. Sodium benzoate is a preservative, particularly in like Mountain Dew and other sodas. So again, you can see how benzoate is the conjugate base of benzoic acid. Notice there's a space between benzoic and acid. But if we go back to the methanoic and ethanoic, you can see how those are derived from methane and ethane, 1 carbon and 2 carbon acids. And we're going to count the C in the CO2 as part of the carbon chain. So here are some examples. Left to right, you can see 4-amino butanoic acid. This butanoic acid because there are 4 carbons there. Aminos we call that the amine group is a number 4. So the carbon of the carboxylic acid is always carbon number 1 in our numbering system. At the end of this video, we'll talk a little bit about priority and why it's an amino acid and not an acid amine. Old school nomenclature, you would count carbons count carbons away from the CO2H, so alpha, beta, gamma, and so that's where you get GABA, gamma-aminobutyric acid, really important in neuroscience. Other examples, so phenylacetic acid. Here, phenyl is a substituent off of the acetic acid as the main root name of it. Trans-2-butenoic acid, so there we have a double bond in the chain, so it's a butenoic. You could also say but-2-enoic space acid. Don't forget the trans. And ammonium formate. So here we're essentially naming it as a salt. So ammonium is the cation. Formate is the anion. Again, that's a carboxylate anion derived from formic acid. So the conjugate base of formic acid is formate. Okay. Okay, so let's keep going. So these are amides. So amides are essentially kind of named as acid derivatives. And so the one on the left, you can call that ethanamide because it's a 2-carbon amide. Or you can name it as an acetic acid derivative. So it would be acetamide. In the box is a really, really common solvent, so we're going to memorize it or /learn it. So learn it. This is DMF, dimethylformamide. Technically speaking, it's usually written with the NN to specify where the methyls are. Where Could the methyls be otherwise? I don't know. But here, if there are substituents on the nitrogen, we just say NN to show that the substituents are there. Dimethyl, formamide, because the left side of it is a formic acid derivative, right? So this part looks like formic acid. Okay. So what's special about amides, remember, is that the lone pair here is conjugated to the pi orbital, right? And so what that means is that this orbital overlap is a stabilizing force, so we want to keep it. So if we rotate around this single bond, we would end up breaking that overlap, and that would make it quite a bit less stable a compound. That's a hill we would have to go over. There is a midterm question to this effect. Okay, so suffice to say, and this is kind of a special thing about amides, is that the lone pair is pretty strongly conjugated to that pi bond. Okay, here are a few other amides we can name. So again, N-ethyl. We're going to name the substituent on the N first. N-ethyl butanamide. So it's a 4-carbon carboxylic acid derivative. So that's where the butan comes from. N-ethyl butanamide. Here we've got 2,2-dimethyl propanamide. So we could name this as an acid derivative, but the common name for the acid is kind of hard to remember. It's pivalowil, whatever. So we're going to name this IUPAC style. So it's a 3-carbon carboxylic acid derivative. So that's a propanamide. And then remember, the acid carbon is always carbon 1. So this is 2,2-dimethyl because there's 2 methyls on there. And again, the 2 tells us that the dimethyl isn't on nitrogen this time, it's on the carbon number 2. If we have ring compounds, so this is benzamide. It's a benzoic acid derivative. And usually we would, in this case, we would count around the ring. So we'd count this carbon as carbon 1, and then we'd say, whoops, carbon 2, carbon 3. So this would be 3-chlorobenzamide. Again, this is one of the only cases in which we're not counting the carbonyl carbon as carbon 1. And just to throw this in there, amide is also what we call NH2-, which if you squint hard, you can kind of see how historically that might have happened, because we treat this as sort of NH-, the rest of it plus. But sodium amide is the conjugate base of ammonia. Esters are like amides. We've got an alcohol, we've got an oxygen here instead of a nitrogen. They're usually made from alcohols and carboxylic acids, and then we lose water. So like this used to be ethanol, this used to be acetic acid, both derived from corn, and then we combine them and drive off water, and that gives us an ester. We're going to always name the alcohol piece first. So we're going to name this as a piece, as a substituent, and then we're going to name this other piece like it was a carboxylate, like the conjugate base of a carboxylic acid. Generally speaking, esters smell nice. They're pretty volatile, often used in flavorings and perfumes. We're going to make some in lab coming up, and it's going to smell really nice. Some of it is banana candy stuff, so let's look forward to that. Esters can't hydrogen bond, and so that's part of the reasons why they're usually pretty volatile. But again, the most common is ethyl acetate. We'll get to know that really, really well. Ethyl is the piece that's connected to the oxygen, used to be an alcohol. Acetate is the other part that used to be acetic acid. An IUPAC name, we would just name the acid ethanoate instead of acetate. In the same way, methyl benzoate. First you name the piece connected to the oxygen, methyl, then you name the other part as part of an acid. So this is a benzoic acid derivative. Methyl benzoate. Note the space between these two things. A little more complicated. Here we're going to name the piece connected to the oxygen first. This is an ethyl group because there's 2 carbons. We're always going to name the carbon connected to the oxygen is going to be number 1. So this is 2,2,2-trifluoroethyl. And then over here we've got a 6-carbon carboxylic acid derivative, hexanoate, 2,2-trifluoroethyl hexanoate. Over here it's a little more complicated. We can take it piece by piece. The piece that is connected to the oxygen comes first as a piece. That is a phenyl group. And then here we've got an alkene. So it's going to be trans-pentenoate. Pentenoate. And then there's a 4-methyl group there. Again, counting from the carboxylic acid. 1, 2, 3, 4. Pentenoate. Okay. Nitriles. Nitriles are similar to amides and esters. They don't look similar, but they're similar in reactivity, and they are also derived from carboxylic acids. So we're going to name them in a similar way. They can't hydrogen bond to themselves, but because they can accept hydrogen bonds, some smaller nitriles, like the most common one, acetonitrile, actually are miscible in water. As a substituent, if it's just by itself, we're going to call it a cyano group. It by itself, CN is cyanide, HCN is hydrogen cyanide. Cyanide is, in fact, as poisonous as you have read about or seen on TV. Nitriles themselves, usually we don't break that CC bond too early, so there's not too much free cyanide in acetonitrile. Again, acetonitrile, it is derived from acetic acid, so we're going to count these 2 carbons and think of it like an acetic acid derivative, acetonitrile. If we're naming it IUPAC style, it's ethane nitrile. So not too clever or elegant, but that is how IUPAC does it. So just name the 2 carbons ethane nitrile, no space. Okay, this is kind of a tricky one. The key here is that, and we're going to talk about like what makes the most important functional group. Here, our most important functional group is nitrile. So we're looking for the longest chain that contains our nitrile. So here, that's a 5-carbon chain. If you count the C in the nitrile, so 1, 2, 3, 4, 5, that's a pentane nitrile that has a methyl substituent and a propyl substituent. So 2-methyl, 2-propyl pentane nitrile. Much like carboxylic acids, the C in nitrile is always carbon 1. Benzonitrile is another really common nitrile doesn't know. Again, it's benzo because it's derived from benzoic acid. So here's an example. Again, we'll learn priority rules in a few slides, but the benzoic acid, the acid down here trumps the CN, and so now we're going to name this as a piece on something else. So this is carbon 1, 2, this is 3 cyanobenzoic acid. And again, HCN, hydrogen cyanide, it's conjugate base, KCN, potassium cyanide, very dangerous. Particularly potassium cyanide, if you treat it with acid, it just goes right back to this gaseous, deadly poison. So watch out.